All right, welcome back, students. Today we are going to be working on 8.5, and we are going to be working with similar triangles. So we're on page 271, and we're going to be taking some notes on page 271. So yesterday we found out that if you have two if you have two angles that are the same, you know that you have similar triangles. So this is known as angle, similar triangle theorem. And today we're going to learn two more theorems to find out if triangles are similar. Now, here's an interesting thing we're finding similar figures. Now, similar figures are figures where side lengths all have same ratios. So the side lengths aren't the same. It's that when you compare this side to this side, and when you compare this side to this side, you're going to get the same ratios. And when you compare this side to this side, you're going to get the same ratios. The ratio of these two to these two is going to be the same as the ratio of these two. Okay, we learned all that yesterday. So today we're going to learn two more. And the first one is side similarity theorem. So don't forget, there's going to be something different that we learn later, and that's side congruency theorem. But right now we're doing similarity. So similarity always has to do with ratios. It has to do with ratios, not with side lengths. It's the ratio of the side length, not the side length itself. So what this side ratio similarity tells us, I know it's written right here, but we are going to write it again, is that if the ratio of AB to RS equals the ratio AC to RT and CB to TS, if those ratios are all the same, then what we have is side similarity. Okay, so I'll show you what that looks like. So let's say we have a triangle like this. So I'm going to give you some side lengths. Say we have 8, 12, 16. And then let's say we have let's say we have 12, 9, and 6. Okay, this is A, B, C, and this is D, F, E. So the triangle ends right here. Okay, now the first thing we'd notice is that, hey, the hypotenuse is up top here and the hypotenuse is down here, right? The longest side length is here at the bottom, the long side length is here at the top. Now, it's difficult for my brain to match sides to sides when I don't have them oriented the same, like these two are oriented the same. So what I'm going to do is I'm going to actually move this one so it's oriented the same, in that the smallest side is on here, the largest side will be here, the medium side will be here, and the longest side on the bottom. So I have to flip this, so it's going to end up looking like this. Oh gosh, why do I keep doing that? I need to start using a pencil. So now my E just went to the top, my F stayed over here, and my D is over here. So I have DE is 6, EF is 9, and DF is 12. So now what I have is I have the exact same triangle, but I oriented it the same way. So I have the shortest side length, the mediumest side length, and the longest side length. Okay. So what I'm going to do is I'm going to do my ratios. I have 8 to 6, and we're going to see if it equals 12 to 9, because again, I'm comparing the same. I'm getting the ratio for the corresponding side lengths. So if I simplify 8/6, I can divide both of those by 2. And so I get 4/3. Divide both of these by 3. 12 divided by 3 is 4/3. Divide both of these by 4. So because my ratios are the same straight across, all my side length ratios, one side, two side, three sides, the ratios are the same. I have a side, side, side similarity. So I know that these are similar triangles. Okay, so there's your notes for page 271. And that's how we know these two triangles are similar, is because the ratios are the same for each of the sides. And now we're going to go into our last theorem, which is side angle side theorem. And I'm going to give you a different one. So let's check this out. We're going to have, this will be 4, 6, we don't know. And this will be 6, 9, and I don't know. I'm going to tell you that this is 100, and I'm going to tell you that this is 100. So for us to have a side angle side ratio, we have to have similar ratios on side lengths, and the enclosed angle. Enclosed angle is the angle between the two side lengths. So I can't work with this one or this angle. Just with this angle, the enclosed angle, the angle in between the two side lengths that we're working with. So 4 to 6, there's that. And then does that equal 6/9? Divide both those by 2, I get 2/3. Divide both those by 3, I get 2/3. So my ratio for two of the side lengths is the same, and my angle is the same. So side lengths ratio same, angle is the same, side length ratio is the same. So I have side angle side similarity theorem. There you go. That's how you do it. Now you get to go through your homework. For 1 and 2, you're deciding whether RST, so you have two problems here, whether this is similar to this, RST and RST, and you are deciding if this triangle is similar to this triangle, and then if this one is similar to this one. Okay? Ooh, and then we might have to solve some. Here we have to find the value of x that makes this similar, that makes these similar. So essentially, if we flip this over, this side is similar to this side, this side is similar to this side. So 3 over x plus 7 equals 3 minus x over 8. So there's the start of your equation. If these are in fact similar, I would have a ratio of 3 over x plus 7 equals this one first, 3 minus x over 8. And then I would go ahead and solve that. Multiply this times this, multiply this times this. Now what I could do is, if I didn't want the x's, if I didn't want to deal with x's on both sides, I could deal with these two sides. So I could have 3 over x plus 7 is equal to the ratio of 5 over 20 over 3. So you could do that too. So you can solve either one of these and you'll find the value of x. All right? Give those a go. Let me know how you do. And please ask me if you have any questions.